Hi, my name is John and welcome to another edition of Statistics Quest. For those of you who follow Jeopardy, and maybe those of you who don't, you know that Amy's streak came to an end at 40, and I thought just for fun we'd look at some probabilities after the fact. So we're going to look at what is a reasonable guess as to the probability of winning any given match. We're going to look at Bayes' theorem. And Bayes' theorem is a way to update probabilities, and we're going to use a particular distribution called the beta distribution. And before I go further, I'm going to talk about a few advanced topics, and I really am only doing that as a lead-in to the final probabilities we look at. So don't get too hung up on some of the concepts along the way. They're kind of beyond the scope of what we're doing here, but I do want to pay them due diligence to show how we end up arriving at a formula that we use. And we'll see at the end the formula is actually very easy to use. Okay, I'm going to look at a few scenarios just as a lead-in to this probability, and then we'll use the formula to plug in numbers to establish a probability. So, okay, first of all, what do we mean by distribution? Well, an easy example are IQs, right? So here's a picture of IQs along with associated probabilities. You see it says mu equals 100, right? That means mu stands for the mean or the average, so the average IQ is 100. And this actually is a probability distribution. So, and in fact, when we deal with these distributions and we find probabilities is that the area under the curve corresponds to a probability. So, for example, if we want to find the probability of a person having an IQ between 125 and 130, we would find the corresponding area between 125 and 130. Let's say it's 3%. Then we would say the probability between 125 and 130, as far as IQ goes, is 3%. Okay. So coming over here, we look at a couple scenarios with the beta distribution. Now this, again, normal distribution is much easier for people to grasp. A lot of you are familiar with that. Many of you have never even heard of beta distribution, let alone seen any pictures of it. With the beta distribution, we have a couple Greek letters involved. One is alpha, one is beta. I made up a scenario where alpha is 6 and beta is 3. Okay? And this is actually the distribution that you arrive at for those particular alphas and betas. Again, why we get at this distribution, don't worry about, just kind of take my word for it. In fact, there are places on the internet where you can plug in different alphas and betas and get different distributions. You'll see the picture of them. Okay, here's another example where alpha is 3 and beta is 6. Now, this one is relevant to the context of what we're discussing, and here's why. We're talking about Jeopardy, right? There are 3 people that play Jeopardy on any given night. And if we didn't know anything about any of those 3 people, what would we say their chance of winning a match is? Well, there's one person, and there's 3 people, so we would say it's 1 out of 3, which is actually 0.33, at least rounded to the nearest hundredth, or 33%. And in fact, notice the cluster of values. There's a large area, i.e. probability, around 0.33. So, and in fact, intuitively, if we think, let's just say we meet 1,000 prospective Jeopardy players, and, you're going to have some smart people, knowledgeable people, some not so knowledgeable, but what is their real probability? Okay, well, nobody really knows, but we can take educated guesses. Many of them are clustered around 0.33. Some of them might be 0.4. Some of them might be 0.2. Let's just say somebody, they never study and they just happen to get lucky to get on Jeopardy. Maybe theirs is 0.01. They're a big underdog because they don't know very much. Okay, and on the other extreme is you have some people that, they're very bright. They study a lot. People like Amy, Ken Jennings, etc. So I made up an example. We talked about the probability corresponding to an area. And if we did want to use this distribution, okay, and we found the area between 0.8 and 1, which I didn't find. This is just a made up number. But let's just say it's 1 out of 1,000, okay? And we say, well, does that seem reasonable? Well, we look back at Jeopardy history, and I think there have been about 8,000 games, right? And there's been Ken Jennings, James Holsizer, Amy, etc., that have gone on very impressive streaks. And we might think, well, yeah, okay, maybe it's a 1 out of 1,000 chance. That seems kind of reasonable that, a select few players, i.e. Ken Jennings, has a real expected win percentage on any given night somewhere in this range. So the upshot of what I'm saying is this distribution, being that a lot of these values are clustered around where we want them to be, seems reasonable pertaining to Jeopardy. And I just kind of did this as a check. Had this been 1 in a billion, and we say, well, wait a second, if it's 1 in a billion, and that doesn't seem reasonable because we think that Ken Jennings and Amy and maybe a few others, their real probability has been in this area, then, it's kind of rare that several people hit that 1 in a billion chance. But I haven't done the math behind it, but it's not 1 in a billion, I'm quite sure. But, it might be something like 1 in 1,000. But anyway, so, all right, enough of that. Again, this is kind of beyond the scope of what I intend on doing. Let's get to the number crunching. What was Amy's updated probability? Again, this is, Bayesian thinking is updating probabilities. And to do that with the beta distribution, it's actually very easy. We needed to arrive at alphas and betas to plug in numbers. The numerator is alpha plus the number of successes. The denominator is alpha plus beta plus the number of attempts. Alpha, we said, was 3. Beta was 6. So the numerator is 3 plus 40. That's the number of successes. The denominator is 3 plus 6. That's beta. 40 is the number of attempts. That's 43 out of 49. That's approximately 88%. So we're saying, with the assumption of the distribution being here, alpha being 3, beta being 6, Amy having won 40 in a row, her established or updated probability of winning any given match is 88%. And that seems reasonable. Actually, last week I did something on this, and I took a stab, and I think I said, one scenario is maybe she has a 90% chance of winning. That was actually prior to doing any of this number crunching. So we established it at 88%. So now we ask the question, what would, this is say, prior to going into her 41st match, and you're wondering, what's the probability that she catches Ken Jennings? We would say 0.88 to the 35th power. Why is it 35? Because at 40, she needs 35 more to get to 75, which would eclipse Ken Jennings by 1. That is approximately 0.01. So going into her 41st match, she had about a 1% chance of catching Ken Jennings. Some of you might think that's low. You might think, boy, she had won 40 in a row. I mean, there's no reason she couldn't do another 40. That's true, but sometimes things are a little bit misleading. You went on 40 in a row. It's kind of a lot like a baseball streak, right? A baseball hitting streak. I remember when Pete Rose, I think he had 44 in a row. He was trying to catch Joe DiMaggio, and people were thinking, man, he's got a real shot. And we could do the same thing with Pete Rose and catching Joe DiMaggio, and I'm sure that's been done. But anyway, the point is, it's harder than you think. Nonetheless, she went on an incredible run, but Ken Jennings is even more incredible. So anyway, I hope you like this episode of Statistics Quest. And again, if you have any questions on anything related to what I did, I know I kind of brushed through some of these advanced topics, but I wanted to get to the final result, which I did. Anyway, so I'm going to sign off here. If you did like it, this edition, please feel free to like it or ask any questions or comments, and I'll see you next time on Statistics Quest.